Okay, today we're going to talk about the work of a force. We're going to start the chapter on work and energy. So in physics you probably recall that work is equal to force times distance. In dynamics we'll have to integrate this a little bit, or we may have to integrate it, but we'll go a little bit beyond what you did in physics. Anyway, we're going to use the capital letter U to designate work. So U from position 1 to 2 is equal to the integral of the force times dr. Dr will be a generic term for distance in any direction, and we may have to integrate that. So anyway, what we'll do is we'll define positive work is in the direction of motion. So if it's going in this direction, work in that direction will be considered positive. Applied forces cause positive work in the direction of motion. And the line of action is what counts. And here's what I mean about the line of action. If I push this box with a force F and go a distance, I'm going to say that the work is equal to the force times the distance. However, if I'm pushing at an angle, only the cosine component is actually causing work in the positive direction. So I'm going to say that this is going to be the work is equal to force cosine. The cosine would be that piece of it times that distance. If I'm going up a hill, again, only the cosine component would be causing work, and we don't care about at this point in time, we don't care about the fact that it's changing elevation, because we're going to say that the cosine component in this direction times this distance is going to be the work caused by the pushing force. It doesn't matter what that angle is, but it's just the cosine of this angle that's going to cause work in that direction. Obviously, the sine component in this direction does no work because it's not pushing in any direction, or it's pushing in that direction, but it's not having any displacement in that direction. The same here, the sine component pushing down, since it's not having any displacement in that direction, it causes no work. All right, so the things we'll have to consider here, the units are going to be in Newton meters. A Newton meter is a joule, or in the English system, it'll be foot-pounds. Okay, now if we happen to have a situation where force may be a function of distance, we may have to integrate it. And let's just say in this case, force is 20 times the square root of s. So then the work would be the integral of 20 times the square root of s, and you can see how I did the integration there. And again, what we'll do to evaluate the magnitude of the work is we figure out how far it moves and just multiply or just plug it into any of the equations that we've developed here, and we can find out what the magnitude of the work is. Okay, now the other thing to be cognizant of this time is that work or the path or the distance may be something odd. It doesn't have to be in a straight line. It doesn't have to be a straight line on an inclined plane. It could be anything. So in other words, this total distance will be the distance s that it moves. And as long as the force is in line and tangent with the direction of motion, then it will always cause positive work along the path. Okay, so in dynamic systems, we're going to say that work causes an increase in kinetic energy. And this comes from our Newton's second law, so I'm just going to say that F equals ma. And using the term, or using the form of ADS equals v dv to define my acceleration, I set this term or this equation equal to a and plug it into there. So now I have force is equal to m times v dv over ds, which is right there. I can bring the ds over to that side, and I see fds is equal to mv dv. I can integrate both sides. The integration of fds is the definition of our work. That's what we just talked about. Pulling out the mass of this side of the integration, I can see that this is going to be 1/2 mv squared, gone from v1 to v2. So I can say that 1/2 mv squared 2 minus 1/2 mv squared of velocity 1 is what we are doing with our work. In other words, the work causes the change in those two terms, and that is 1/2 mv squared you'll probably recognize as kinetic energy. In our book, we'll refer to kinetic energy with the capital letter T. So basically it says that U will cause changes in kinetic energy T2 minus T1. All right, now this is called the kinetic energy equation then. T1 plus U is equal to T2. That's will be used if only kinetic energy is involved. All right, so positive work to a system causes increase in kinetic energy. Negative work decreases T. Energy is the capacity to do work. These are probably things you remember. Maybe you haven't done this before, but energy is a scalar. That means that there's no direction associated with it. It is always positive, never negative. Now you can have negative work, but you can never have negative energy in our definition. Okay? It's a scalar, we have no directions, and so it doesn't matter if it's going up or down or sideways, the kinetic energy will always be a positive number. Or if it's not moving, kinetic energy will be 0. All right, the next thing we want to talk about is stored energy. Stored energy is potential energy, and we're going to use the capital letter V for stored energy. And we'll have two types of stored energy, which we'll talk about, but we're going to suggest that the work caused by forces that change potential energy are going to be called conservative. Conservative means you get all that energy back. You can and they can be conservatively converted to something else. So there are no energy losses with conservative forces. And so conservative work causes conservative change in potential energy. All right, I know that's a lot of words for right now, but we'll get used to dealing with the difference between conservative and non-conservative forces. So the first type of conservative change of energy we want to consider is gravity. So let's suggest that you have a box that weighs 10 pounds here and it's sitting on the table. Now we raise it up a position height, up a position to a different height. You can see that we have changed the potential energy. Again, this should be a review from physics, but the change in potential energy is mg, which is 10 pounds, times the height, mgh. And we'll find that that the greater the potential energy means you have is at a greater height. So in other words, if you move it to a higher position, you have increased its potential energy. So gravity, the change in potential energy for weights or forces or masses due to change in height will be the change in potential energy will be mgh. All right, we'll talk about springs in a later section next time, but the springs are also a type of potential energy, and their force is F is equal to Ks. All right, so just to sum up then where we are today, or right now, we're going to say that conservative forces cause conservative work, and those are going to be exhibited in gravity and springs. And what we'll do is we'll always refer to gravity and springs as part of our potential energy. Non-conservative forces are going to cause non-conservative work. And those kinds of forces are friction, pushing or pulling forces, anything that you're pushing or pulling on your object that you're moving. Which gives us then our general equation is T1 plus V1 plus U non. And what I mean here is these are the work due to non-conservative forces is equal to T2 V2. Again, T1 or T is equal to kinetic energy, and we call that 1/2 mv squared. V is going to be equal to gravity, which we'll call mgh, and springs, which we'll talk about next time. And non-conservative forces are going to be the sum of the integral of f ds. If we have to integrate, we'll have to do that, but there may be lots of different forces that we'll have to add together, some of them positive, some of them negative, to come up with the work that we will be doing. Okay, so this is the takeaway equation. That's the equation we'll use every time. All right, so let's look at just a very simple example. Let's say we have a 50 kilogram box sitting on the floor, and we're going to push it with a 200 Newton force, and we want to move it 10 meters. What's the speed or the velocity at the end of that? Well, here's our equation. V1 plus T1 plus U non, and I'll put non right there, is equal to T2 plus V2. All right, what is our V1? Well, V1 is potential energy, and we're going to say that it's sitting on the table, so it has no beginning potential energy. T1 is our beginning kinetic energy, 1/2 mv squared. In this case, it is starting from rest, so that term is going to be equal to 0. F times S is going to be our non-conservative force, so it's going to be the pushing force times the distance we move it. And in the end, I'll have a T2, which is 1/2 mv squared, and I won't have any change in potential energy, so that term will be 0. All right, so I add these all up. Z0 plus 0 is 200, my pushing force. I've pushed it 10 meters. 200 times 10 equals 1/2. The mass is 50 kilograms times the velocity, and I solve that for the velocity, and I can get 8.944 meters per second. Okay, very simple. And just note that friction causes negative work and acts through the distance traveled. So here's another little picture. We're going to say the same thing, except that in this case we have a mu of 0.4, and we're going to start with the same terms over here, T1 and V1, and those are both 0. Now I'm going to say that U is equal to the sum of all of the forces and the distances through which they move. In the end, then we're going to have a 1/2 mv squared for T, for the kinetic energy, and still no change in potential energy. So again, we'll put in the numbers. We're going to say that we have our pushing force, 200, and it goes our 10 meters again. I didn't put the 10 meters on my picture here, but I probably should do that, 10 meters. Now in this case I have a friction force pushing backwards on it. Well, normal force here is going to be equal to mg because it's sitting on a flat. So my friction force will be equal to mu normal. So I said mu mg, and that also acts through a distance of 10 meters. So those acting together is going to equal our 1/2 mv squared. Here it's real important to honor the equal sign. When you put everything together, I want everything on this side of the equation until we get done with filling in all the blanks. Everything on this side of the equation until we get done with filling in the blanks, and then you can do your algebra and solve for V. So again, quite simple. Recall again that force of friction is equal to mu normal when slipping or impending slip, and we'll deal more with friction as we go along. But there's obviously a chance when force of friction will be less than mu normal if it is actually not slipping. In all of our friction problems in general, we're going to be moving, and if we're going to be moving, then there's going to be a friction that's slowing it down. Again, it may not be, if it's a sliding friction, it's definitely going to be mu normal. Here's a little example problem of energy in action. Energy is definitely a valuable tool. It's a good shortcut. And it's the special conditions are when forces and distance and velocities or speeds are involved. Energy can be a great shortcut versus F equals ma. F equals ma can always be used, but we may find that energy is handy. So anyway, let's talk about this guy. The truck is driving along and he slams on his brakes. He's only going 10 kilometers per hour, which isn't very fast, and it only takes a 1/2 meter before he stops. But our question is, how far will he slide if he's traveling 80 kilometers per hour when the brakes are applied? So little force free body diagram. We're going to say he's going in this direction. He's got an mg here, normal force pushing back, and in this case the force of friction is going opposite his direction. And we know that the force of friction is equal to mu mg because it's on a flat plane. And the work due to the friction is negative because the force is in the opposite direction of the displacement. The displacement is the s going in this direction. All right, just a couple of conversions here. We're going to say that the force of friction is mu normal is equal to mu mg. And 10 kilometers per hour, we'll want to deal in meters per second, is equal to 2.778 meters per second. 80 kilometers per hour is 22.22 meters per second. All right, so we want to set this up in 2 stages. The first stage suggests that we're going to do our energy equation, and this is on his 10 kilometers per hour speed. I'm going to say that T1 plus V1 plus U naught is equal to T2 plus V2. Let's start with the end. What's happening at the end is he stops. So the ending condition is going to be 1/2 mv squared, except that that's going to be equal to 0. There is no change in the elevation, so both of the potential energies in this case are going to be equal to 0. So let's start with our beginning equation over here. T1 is 1/2 mv squared, so I got 1/2 the mass times the velocity of 2.778 squared plus my beginning potential energy, which is 0, and minus friction times the distance that it moves. We're given the distance that it moves is 0.5, and again our ending condition is 0. So I can solve this for the force of friction. I don't know what my mass is, but I can solve this for the force of friction is equal to 1/2 m my velocity squared divided by the distance, putting that over there, and I can say that force of friction is 7.716 times the mass. All right. Now, using that in our second piece, we're going to suggest that the 80 kilometers per hour, he's got the same equation, T1 plus V1 plus U naught is equal to T2 plus V2. Again, I've got a 1/2 mv squared, no V, or no potential energy. I got the same force of friction, and I'm going to bring that in from here, but it's going to act through a different distance. So this is the distance I'm trying to solve for going at a higher speed. Again, I'm ending at 0 and ending at 0 potential energy. So again, I'll do 1/2 mv squared minus my force from up above, and bring that in times distance s, and I can solve that for s, meaning 32 meters at traveling at 80 kilometers per hour. So that's quite a bit different. It took us 1/2 meter to stop at 10 kilometers per hour. Admittedly, that's not very fast, but it only takes 18 inches to stop. In this case, it takes over 30 meters to stop at 80 kilometers per hour, which still isn't very fast, really. 80 kilometers per hour is kind of maybe about, didn't calculate this, probably about 45 to 50 miles per hour. So again, not real fast, but it takes over 30 meters to stop. And you wonder, man, that is really a lot of distance. Well, if we were to think about this in terms of F equals ma, we would have the velocity squared function involved. And again, we have velocity squared function here too. From 10 kilometers per hour to 80 kilometers per hour, we have 8 times the speed. And since it's a velocity squared function, we should expect that it takes 64 times as far to stop. So if you look at 0.5 meters here and 32 meters here, well, clearly that's 64 times. So it gives us the answer in a little bit faster method than using the F equals ma approach. Now, what is the coefficient of friction? Well, we should know that force of friction is equal to mu mg. Force of friction that we solved for up here was 7.16 times m is equal to mu mg. The m's cancel, and we can see that mu is equal to 0.7865, which is probably about right for a car or truck. It's maybe a little higher with than we would see with kind of street kind of tires, but probably would expect something close to that. All right, here's another problem. This is a little inclined plane problem, so we're going to definitely have some potential energy to resolve here. So we're going to say that this box is on this inclined plane. It's going to have a tension caused by this motor at 300 newtons. The box itself has a mass of 20 kilograms. And what we're going to say is it's starting from rest, and we're going to crank on this motor and start pulling it up the hill. And we want to find out what the what the speed is after 10 meters, and it's got a coefficient of friction of 0.3. All right, in inclined plane problems, in fact, if any elevation change problems, we're going to have to set up a datum. And the datum is where it's either at the start of the problem or it's the end of the problem, but basically datum means 0. So let's write or draw our free body diagram of our box, and we're going to say that it's sitting here on an inclined plane. It's got an mg coming down. In the direction of the plane, we're going to have an mg cosine of 30 degrees, because that's what our angle is, 30 degrees. We're going to be pulling it up the hill for 10 meters. That's going to be our positive direction. And I've got a normal force resisting that mg cosine theta, and since I'm going in that direction, my force of friction, which will be mu normal, will be opposite my force up the hill. My change in elevation, this is where the datum comes in. I'm going to start here at 0, and I'm going to move uphill. This uphill distance is going to be 10 times the sine of 30. So with that, I can say this is my beginning potential energy, that's my ending potential energy. Let's write our energy equation. T1 plus V1 plus U naught is equal to T2 plus V2. Again, I'm starting with at rest, so I don't have any mv squared, any 1/2 mv squared. I'm starting with my datum at 0, so my beginning potential energy is 0. My ending kinetic energy will be 1/2 mv squared, and that's what we're trying to solve for, is my ending speed. My ending potential energy will be mgh, as we referred before. Starting from here, moving up to here, I'll have an mgh, and I can calculate that straight up. I'm going to say that my mass is 20, my g is 9.81, and my height that I moved up is 10 sine 30. The work. What is the work? Now, just a note about V's. We're going to use capital V for potential energy, but obviously small v for velocity. So in your problems, just be really careful how you call those v's and make sure you don't get mixed up. In my examples, I'll try to be pretty careful about drawing big capital V's here for potential energy and a little smaller v's for that. Unfortunately, we don't have a different letter. This is the letter we're going to be using. All right, let's talk about the work. The work is not conservative, which means that it is going to be pushing, pulling, or friction forces. So what pulling force do I have? Well, I got a 300 pulling it up the hill, so that's going to be my pulling force. It's going positive because it's going in the direction of motion, so that's positive. The force of friction will also be going in that direction, but it's a negative. It's pulling in the opposite direction, so I'll have force of friction times 10. Plugging all the numbers in here, I'll say 300 times 10 minus mu mg cosine 30, theta is 30, times 10. And I plug all those into my big equation. Sometimes it's helpful to write the terms out kind of this way instead of put everything into the equation this way. The equations get pretty long, and sometimes you know, you'll have a wraparound equation if you put all the pieces of your terms in the one equation. So sometimes it's helpful to maybe do some intermediate calculations, and then when you write your equation like this, it makes it a little easier. But anyway, so let's go ahead and fill in the blanks. We've got T1 plus V1 plus U non, T2 plus V2. So I've got this one is equal to okay, so that's 0, so this is going to be my U non, so that is 3,000, minus the force of friction is 0.3 times 20 times 9.81 cosine 30 times 10. That's going to be equal to my T2. So it's 1/2 mv squared, but in this case I'm going to have a change in potential energy of mgh. Putting all those together, then I can solve for my V2, my velocity at stage 2, as 12.285.